Now that we have talked about how catalysts are deactivated, we also want to talk about how to regenerate them. Regeneration is an important aspect of catalytic processes. We do not want to throw away spent catalyst. Catalysts are usually expensive, and we do not want to be using fresh catalysts every time. So we want to regenerate them ourselves if possible. For coked catalyst, it is possible to regenerate them by reacting the carbon deposits with oxygen by passing hot air or oxygen over the catalyst pellets. As we saw in previous slides, coke is mostly carbon and other carbonaceous compounds. So we can regenerate the catalysts simply by burning the coke. This figure shows how a completely coked catalyst pellet is regenerated over time. In this process, catalyst pellets go from being completely coked to fully regenerated as the outer layers of carbon are reacted away, leaving smaller and smaller cores of coked catalyst until it is eventually all removed. Typically, what you would like to determine is the amount of time that it would take to completely regenerate the catalyst. So we need to model how the size of the core of unreacted coke changes over time. By core, we mean the black regions in the diagram, which are the unreacted coke. The model that we use is called the shrinking core model because, as you can see here, we have a core of unreacted coke that is shrinking with time. So here we can see a diagram of the coked catalyst pellet that is being regenerated by burning the coke with oxygen. The catalyst pellet has a radius R0, which is also the radius of the core, or unreacted coke at time equal to 0, when the pellet is covered completely with coke. Capital R is the radius of the core at time t. The core is shrinking, so obviously you would expect capital R to decrease with time. The core is shrinking because oxygen is reacting with the carbon at the surface of the core, forming carbon dioxide. So the amount of carbon on the surface reduces and the core shrinks. However, remember that the catalyst pellet is porous and the oxygen has to diffuse in from the outer radius R0 to reach the core at radius capital R. And when it does, the oxygen reacts with the carbon to form carbon dioxide, which then needs to diffuse out to the surface of the pellet. Our goal is to derive a mathematical expression for the radius of the core or the unreacted coke. So capital R as a function of time. If we have this expression, then it will be easy to determine how long it will take to completely remove all of the coke from the pellet. As we want to find out how quickly the core is shrinking, we need to set up a material balance for the carbon in the core. However, the rate at which the carbon reacts depends on how quickly the oxygen can diffuse in from the pellet surface to the core. In order to calculate this, we need to set up a material balance for the oxygen in the regenerated part of the catalyst pellet. This diagram shows the catalyst pellet, the unreacted core, and the control volume for our oxygen material balance. Here you can see the outer surface of the catalyst pellet at R0 or R0. And at this point, the surface concentration of oxygen is Ca0. The radius of the unreacted core is capital R. And at this point, we assume that the concentration of oxygen, Ca, is 0. So we assume that the rate determining step is the diffusion of oxygen, and the reaction between carbon and oxygen is much faster in comparison. As soon as the oxygen reaches the core, it reacts with carbon instantly, so there is no oxygen at the core surface. This region between the unreacted core and the pellet surface is called the ash layer. And this is where we are going to write our balance for oxygen. So we draw our control volume here. It is a spherical shell at radius small r with thickness dr. An important thing to remember is that there is no reaction taking place in the ash layer because there is no carbon there. It has already been burnt. The reaction only takes place at the surface of the core, at capital R. We will need this later when we write our balance. So now we need to write our balance for oxygen, and we need to make some assumptions. Remembering that the core is shrinking over time, we cannot make a steady state assumption because the process is a dynamic one. However, to simplify the analysis, we will assume quasi-steady states. So we can assume that the oxygen diffusion process is at steady state. Note that at every time t, there is a different steady state oxygen concentration profile along the radius r. Another assumption is equimolar counter diffusion. So for every mole of oxygen that diffuses into the pellet, 1 mole of carbon dioxide diffuses out. This is so that we can use Fick's law for the diffusive fluxes. So now we will write our material balance for oxygen. And we will denote oxygen as A. Our control volume for the oxygen material balance is here. This is a spherical shell with thickness dr, and it is in the ash layer. Our general material balance is accumulation equal to in minus out plus generation. For oxygen, we can ignore accumulation because of the quasi-steady state assumption. We can also drop the generation term because our control volume is in the ash layer and there is no reaction in the ash layer. So in the ash layer, we assume that all of the carbon has been burnt already. The reaction is only taking place on the surface of the core. So in our material balance, we only have 0 equal to in minus out. So we just have to write the incoming and outgoing flow rates in terms of the fluxes multiplied by the surface area normal to the flow. So as we did with the material balances in the previous topics, we defined flux as positive from the center going out. That is the typical convention in chemical engineering. So again, we defined the flux as positive in the direction of increasing R. So that means that the flow going into our control volume is at R, and the flow going out of our control volume is at R plus delta R. So we'll have 0. So the incoming flow rate to our control volume. So that's the flux, which we will denote as W. So A for oxygen in the radial direction. And we have to multiply this by the surface area normal to the flow. So this is a spherical shell. And for a spherical shell, the surface area is 4 pi r squared. Okay, and this is coming in at R. Okay, so here. And then the outgoing flow rate, so that's the flux of A in the radial direction. Again, we have to multiply this by the surface area normal to the flow. So for sphere, that is 4 pi r squared. And this outgoing flux is at R plus dr. So now we can divide each term by 4 pi delta R. So we'll have 0 is equal to the flux times R squared. So this is at R. We also have a similar term for R plus dr. And we have delta R in the denominator. And then we take the limit of both sides of this equation as delta R tends to 0. And we will have 0 is equal to negative ddr of flux times R squared. So this is just the definition of the derivative. So now we can define flux in terms of the change in concentration. And we can use Fick's law because we assumed equimolar counter diffusion. Okay, so equimolar counter diffusion, then we can use Fick's law to express the flux in terms of the change in concentration along R. So we have negative diffusivity. So again, we have a negative sign here because we defined flux as positive in the direction of increasing R. But the flux is taking place from point of high concentration to low concentration. Okay, so the direction of the flux is from the surface to the center. But our positive flux is positive from the center going out. So we have a negative sign here. So diffusivity times the rate of change in the concentration of A with respect to R. And then we just substitute in this expression for the flux into our equation here. So we'll have 0 is equal to negative d dr. Have dE, dCA, dr, and we have R squared. We can tidy this up a little bit, so we can write this as 0. We can take out diffusivity from the derivative if we assume that this is constant. And we have 0 on the left-hand side. So it will just disappear. So we will have ddr of dCA dr times r squared. Okay, so we can easily solve this. So we can integrate twice to get the concentration profile along R. So this is a second order differential equation. So we need two boundary conditions to solve this. Okay, so looking at our pellets, we can define two boundary conditions. So one at the surface of the pellet, so that's at R equal to R0, and one at the surface of the core. So that's at small r equal to capital R. So boundary condition 1. So R is equal to R0. So this is at the surface of the pellet. And at the surface of the pellet, the concentration of oxygen, so Ca is equal to Ca0. Boundary condition 2. This is at the surface of the core or surface of the unreacted coke. Okay, so R is equal to capital R. We assumed that as soon as oxygen reaches this surface, it reacts instantly. So there is no oxygen on the surface of the core. So Ca is equal to 0 on the surface of the core. So now let's integrate our differential equation. So, okay, so first integration. So this one first. So right-hand side. So I will now put that in the left-hand side of my new expression here. Okay, so the ddr will just disappear if we integrate. So we'll have dCA dr r squared. And the integral of 0 is a constant, k1. And then we can integrate again. We can rearrange this dCA k1 over r squared dr here. Now we can integrate. So the integral of dCA is just Ca. And the integral of this is negative k1 over r. And we need another constant of integration. So we can use our two boundary conditions to determine the constants k1 and k2. So let us apply our second boundary condition first. Ca is equal to 0. So we'll be able to simplify our equation. Okay, so applying boundary condition 2. Boundary condition 2 is at R equal to capital R. So this is at the core. This is at the surface of the core. So 0. Okay, concentration is 0 on the surface of the core. This is equal to K1 divided by capital R plus K2. So therefore, K2 is equal to K1 over R. Okay, so now applying boundary condition 1. Okay, so boundary condition 1 is at the surface of the pellets. So at R is equal to R naught. So in there, the concentration of oxygen is Ca0. So we substitute that in here in our equation. So Ca0 is equal to negative K1 divided by R0 plus K2. But from the previous application of boundary condition, okay, we determined that K2 is equal to K1 over R. So we can factor out K1, okay, and we'll have 1 over R minus 1 over R naught inside our bracket. Okay, so therefore K1 is CA0 divided by 1 over R minus 1 over R naught. And K2 is K1 over R, but we know what K1 is. So K1 is here. So K2 is just CA0. Okay, CA0 divided by 1 over R minus 1 over R naught. And okay, so K1 over R, so we have an R here. So therefore, our concentration profile, okay, so this one, we'll just substitute in the expressions that we obtained for the constants K1 and K2. So concentration profile is Ca is equal to negative K1, negative Ca0, 1 over R minus 1 over R naught. And we have a small r here, plus K2. K2 is Ca0, 1 minus R minus 1 over R naught, capital R. Okay, so we can write this as Ca over Ca0, 1 over R minus 1 over R divided by 1 over capital R minus 1 over R0. To get this from this, we just factored out Ca0 and this term here in the bracket. So we have 1 over R minus 1 over R0. Okay, and then we'll have 1 over R, small r here, minus 1, or this one because we have the negative here. Okay, so this one is capital R, 1 over R. So from this one, minus 1 over small r. So from here. Okay, and then we just transferred Ca0 to the denominator of this. So we obtain this. So this is our concentration profile. This is the expression that we just derived, and this is what it looks like from the surface of the pellet to the surface of the core. The y-axis is the ratio of Ca to Ca0. So again, Ca is the concentration of oxygen at any R, and Ca0 is the concentration of oxygen at the surface of the pellet. So Ca over Ca0 is 1 at the surface of the pellet and 0 at the surface of the core. As you can see here, Ca only depends on the size of the pellet, R0, size of the core, so that's capital R, and the radial coordinates, so that's small r. We can use the concentration profile of oxygen to determine how the size of the core, capital R, changes with time. So now we're going to look at the gas-carbon interface. So that is at small r equal to capital R. And we need to write the flux at the gas-carbon interface. So that is at R equal to R. The flux is, so WAR at R is equal to R. So using Fick's law, so this is equal to negative of the diffusivity times the rate of change in the concentration of A with respect to R. And this is at R equal to R. So we need to evaluate the first derivative of Ca. So we can use our concentration profile here. So how do we get the derivative of Ca with respect to R? So dCA dr. Okay, so we can look at here. So this is Ca. Okay, and we are differentiating with respect to small r. So everything else we can take as constants. Okay, so we can write Ca0. Okay, and we also have 1 over r minus 1 over r0. And what is the derivative of negative 1 over r? 1 over r squared. But remember, we are evaluating this derivative at r equal to capital R. Okay, so we'll take the derivative of this. Derivative of negative 1 over small r is positive 1 over r squared. But we will change small r to capital R because we are taking the derivative at r equal to r. So we can write r squared here. Okay, so the flux of A in the radial direction at r is equal to r. So we just substitute this in to this expression. So we have negative of the diffusivity times Ca0 divided by 1 over r minus 1 over r0 times r squared. So we will need this later when we write our balance for the carbon. Now we are going to write our carbon balance. And for this, our control volume is the whole of the core. Our material balance is accumulation is equal to in minus out plus generation. So just the general material balance. Since there are no carbon going in and out of our control volume, we can drop the incoming and outgoing flow rates. So our material balance is just the accumulation term equal to the generation term. So let's write the accumulation term, ddt. And inside the bracket, we need to write how much carbon is inside the control volume. So we can write the volume of the core easily. So that's 4/3 pi r cubed. So note capital R, volume of the core. And then we can multiply by the molar density of carbon. So volume times the molar density of carbon. So that will be the mole carbon inside the control volume. So rho C is the molar density of carbon. So this is in kilomole per cubic meter. But not all of the core is carbon. So there are some void space in there, and there's the actual catalyst itself. So there are active sites as well as the supports. Here in our accumulation term, we just need to write it for carbon. Okay, so we need this parameter phi c. Phi c is the volume fraction of carbon in the porous catalyst. So this term here is the rate of change of carbon inside the control volume. This is equal to the generation term. So we have the rate of generation of carbon. So this is mole per second per square meters. So we need to multiply it by the surface area. But remember that the reaction is just taking place on the surface of the core. So we will not use SA because SA is internal area. So here, we just want the external area of the core. Okay, so it's a sphere. So that's just 4 pi r squared. And then we can simplify. So 4 pi on this side will cancel with the 4 pi on the left-hand side. And then we can take some of the constants out of the derivative. So we have rho c phi c over 3. And we have the derivative with respect to time of r cubed. And then on the right-hand side, we have the rate of generation of carbon times r squared. So we can evaluate this derivative. So note that capital R is a function of time. So for this term, we will have to apply chain rule. Okay, so we have rho c phi c over 3. So applying chain rule here. So first, take the derivative of r cubed. So that will be 3 r squared. But capital R is a function of time. So I have to take the derivative of r with respect to time. And this is equal to rc double prime r squared. So we can simplify. R squared here will cancel out with the r squared there. The 3 will cancel out. And we will end up with this expression. So dr dt is equal to rc double prime. Then we have rho c and phi c from this side. So now we need to write rc double prime in terms of r. So how do we do that? We write that the rate of disappearance of carbon, this is equal to the flux of oxygen at the gas carbon interface. This is true because we assume that for every O2 that reaches the surface of the core, so that instantly react with the carbon to form CO2. So for every mole of O2 that reaches the core, 1 mole of carbon will disappear. Okay? So now we write the rate of consumption of carbon. This is equal to the flux of oxygen at the gas carbon interface. But remember that we are interested in the flux that is going into the surface of the core. So we need a negative sign here. Okay, so negative sign here because the oxygen, okay, is going into the surface of the core from the regenerated region of the core into the surface of the core. And remember that we defined flux as positive in the direction of increasing R. So O2 going into the core, yeah, but we defined positive flux in the direction of going out, okay, increasing R. That's why we have a negative sign here. And here, the negative sign here, it's because we're interested in the consumption of carbon. Okay, so this is carbon consumption. So earlier, we wrote an expression for the flux of oxygen at the gas-carbon interface. So we wrote this expression. Okay, and we have a negative sign here. So this negative sign here will disappear. So we'll have, this is equal to diffusivity times Ca0 divided by 1 over R minus 1 over R naught R squared. Therefore, we can write this now because now we have an expression for RC in terms of capital R. So we can write dr dt is equal to, okay, so RC double prime. RC double prime is this. Okay, but you have a negative sign here. So we have negative dE Ca0 1 over R minus 1 over R naught R squared. And don't forget constants here. So we have, so I'll write it here, rho C and phi C. So always check that the right-hand side of this equation is negative. Okay, so always check right-hand side is negative because the core is shrinking. dr dt. This is negative because the core is shrinking. So it's easy to get the sign wrong. So always check that the right-hand side is negative. Yeah, is this negative? So we have this term in the bracket here. So we want this to be positive because we have a negative sign here. So this term here is positive because R naught is greater than R. So this is the radius of the whole catalyst pellet, and this is the radius of the core. So 1 over R is greater than 1 over R naught. So this is always positive. So dr dt is negative. All that we need to do now is to evaluate this differential equation. So we can rearrange this. So I will put all of the terms with R on the left-hand side and the constants and the term with the time on the right-hand side. We'll have 1 over R minus 1 over R naught times R squared. And then we have a dr there. This is equal to negative dE Ca0. Okay, and then we have the rho C phi C in the denominator. And then we have dt from this side. I'm going to multiply each term inside the bracket with R squared. So we'll have R minus R squared over R naught dr. And this is equal to negative dE Ca0 rho C phi C dt. Okay, so you can see that our expression is simple. And we can solve this equation by simply integrating it. So we'll integrate it. Limits of integration. So we have a time equal to 0 to time t. And at time equal to 0, the size of the core is R naught. And at time equal to t, the size of the core is R. So evaluating the integral, we'll have R squared over 2 minus R cubed over 3 R naught. And this is being evaluated from R0 to R. Then the right-hand side, we'll have negative dE CA0 rho C phi C times T. Let's evaluate the left-hand side. At R equal to R, we'll have R squared over 2 minus R cubed over 3 R naught. And then minus at R naught. R is equal to R naught, so we have R naught squared over 2. Then minus, and then we have another negative sign there, so we'll have plus R naught cube over 3 R naught. And this is equal to negative dE CA0 rho C phi C times T. What I can do to tidy this up is I can multiply each term. Okay, so I'll multiply it. So there's a common factor here. Okay, the denominator, so 6. And I don't want the negative sign here, so I'll multiply each term by negative 6. And then I'll have R naught squared here. I would like to rearrange it now so that I'll have the term with the highest exponent first with respect to R. Okay, so this one first, so I multiply this by negative 6 over R naught squared. So we will have 2 R cubed over R naught cube. This one here, so I'll have minus 3 R squared. And then I'll have this R naught squared. And then this term here, okay, multiply by this. The R naught squared will cancel out. So I'll have positive 3. And then here, so I have R naught cube. Here I have R naught squared times R naught. So that's R naught cube. This will cancel out with that. And negative 6 divided by 3, that's minus 2. Okay, and then this side here, so I'll have 6 dE CA0 T rho C phi C. Now I can solve for T. So T is equal to rho C phi C all over 6 dE CA0. And I have this term here. So I can write this as 2 R over R naught raised to 3 minus 3 R over R naught squared, and then 3 minus 2, I have plus 1. This is the expression I want. Expression describes the size of the core at any time t. With this, we can determine the time necessary to consume all carbon. This will happen when the size of your core, the radius of your core is 0. So you just substitute in 0 to the r's in this expression. And the time necessary to consume all carbon we will denote as T infinity. Okay, and this is equal to rho C phi C over 6 dE Ca0. It is useful to write this expression in terms of conversion. The conversion x can be defined as the initial fouled volume minus the remaining fouled volume all over the initial fouled volume. Therefore, x is equal to, pellet is spherical, so initial fouled volume is 4/3 pi r naught cube. And the remaining fouled volume is 4/3 pi r cube divided by 4/3 pi r naught cube. We can cancel out the 4/3 pi, and x is equal to r naught cube minus r cube divided by r naught cube. And this can be written as 1 minus r over r naught cube. Therefore, the ratio of r to r naught is equal to 1 minus x raised to 1/3. So we can substitute this into our expression here. Okay, so just replace r over r naught with 1 minus x raised to 1/3. Substituting r over r naught into our expression for the time and noting that this bunch of constants here is t infinity. So we can write t as t infinity multiplied by, okay, so I'll start with 1 and then minus 3. R over r naught is 1 minus x raised to 1/3, but I have 2 there. So this one will be raised to 2/3. Okay, and then last term would be this. So I'll have plus 2, 1 minus x raised to 1/3, but I have exponent 3 there. So the exponent here will just be 1. So this is my final expression in terms of conversion x. The next slides show what we did on paper. And these are the expressions that we derived. This is the time it takes for the core to reduce to radius r. And this is the time it takes to completely regenerate the catalyst pellet. This is the same expression for the time to regenerate the fouled catalyst, but in terms of conversion x. When the conversion x is 0, so we'll have 1 minus 3 plus 2, so that's 0. So time is 0, which is what you would expect because you start with a completely fouled pellet where the conversion x is 0. When you put x equal to 1, then the second and third terms disappear and the time is t infinity, which is the time it takes to completely regenerate the pellet. I will stop here so you can have a break. In the last part of this topic, we will talk about dissolution of solids, which can also be modeled as a shrinking core.